Um, Science teacher, Mr. Pugsley. How are you today? Hope you're well. What we're going to do is we are going to do a little bit of notes on this topic called periodic trends. This is something that we should have finished before the 9 weeks is over. And so we're right at that edge. And then furthermore, we're going to do a lab on this coming week. So you need to learn this content so that the lab will make sense and you'll make a good grade for the first grade of the new 9 weeks in the lab. So with that said, it's periodic trends. And when we talk about a trend, it's like something that's happening up over and over. and so that's what we want to see here. Let me pause the video for one quick note for myself. Okay, so we are working on that right here. And so we need to learn about some common terms that we're going to be using quite a bit here. All right, and so atomic radius, right? Just like a radius of any circle is a distance from the center to the outside edge of the circle. Well, atomic radius is no different. It's the distance from the nucleus to the center of the atom. Or not from the nucleus to the edge of the atom. Excuse me, I'm sorry. Edge of the atom. All right, that's atomic radius. The ionization energy is the minimum energy needed to remove an electron from an atom. Remember, ions are atoms of an element that have either gained or lost an electron. When we talk about ionization energy, we're talking about how much energy does it take to remove an electron, okay? Some elements we're going to see have a high ionization energy. It takes a lot to remove an electron. And some, like, you can have it, basically, for the amount of energy it takes to remove an electron. Electronegativity is the ability of an atom to attract electrons in a chemical bond. And so how much are they attracted to the electrons in a chemical bond? All right, and so these are words that we're going to use in this right here. And so let's go ahead and start with atomic radius. Okay, if you look at this picture here, I'm going to make this picture a little, if I can, make it a little bigger. Oops, nope, there it is, better. All right, if you go across to the right, this tells you the atomic radius, and this is in angstroms, which are 10 to the negative 10th meters. So this is 0.53 angstroms. This is 0.31. This is 1.51 angstroms. This is 1.12. And as you see, we go down the period, we get smaller and smaller atoms. All right, and if you remember, that's the atomic number goes up. And so even though the atomic number goes up and you get more protons, neutrons, and electrons going down the period, it goes up. And so this is the atomic radius. It goes, it decreases as atomic number goes up. All right. But if you go down a group, the atomic radius increases. All right, that makes a little bit of sense. First is when we go down, you're going to have more orbitals. And so you're going to have a bigger atomic radius. That makes sense. But going across, the reason why the atomic radius is so much is because, first off, these are all the second energy level. That means they're all that second energy level. And so their distance is all about the same distance. But this has got more protons. And so it's going to have a greater pull to the nucleus, and it keeps those electrons close. And furthermore, like oxygen and fluorine only need one more electron to become stable. And so they're holding onto their electrons really tightly. All right. And so therefore, that's why their atoms are smaller. Their atomic radius is smaller. Over here, again, we're going to get smaller and smaller. And again, this is all that third energy level mostly here. And we see it decreases as you go across. All right. And again, reason being, you have this is all these energy levels, these S and P sublevels are all about the same distance from the nucleus, but you get more protons, so it keeps the electrons close to the nucleus. And then furthermore, chlorine is only one away, and sulfur is only two away from having a full outer level. And then argon's already stable, so it definitely doesn't want to get it. So the atomic radius decreases as we go across the period, and it increases as we go down. And it's because of that here. Again, ionization energy. If you remember what ionization energy is from that first slide, yeah, it's the energy it takes to remove an electron, right? Ionization energy here, it increases as we move across the periodic table here. And it increases as we move up the periodic table. Or you could say it decreases as we move down the periodic table. And you start to think, why is that? All right. And again, the same thinking as the atomic radius. As we move across the energy levels, you have more protons, but the same distance from the nucleus. So therefore, those protons, like in the first energy level, are holding tighter to those electrons. It's got two electrons, but you have two protons now, and they hold it a little bit tighter. And so it's a little bit more ionization energy for helium than hydrogen. And as we move across period 2, again, we got the S and the P orbitals. Again, as we move across, we get more and more protons, all right, but the distance from the nucleus has not increased. We get more electrons, but the distance from the nucleus has not increased. So those protons pull those electrons in closer, all right? And furthermore, they want one more electron, or they don't want any more. If like these noble gases, they're already stable, all right? They're all act stable. These halogens, they don't act stable. They're not all stable. They need one more electron. And so they hold on to those electrons very tightly, and they keep them on, and it takes a lot of energy to take one away because they want to keep that electron because of that. Whereas the elements over here on the left, they have a low ionization energy, like for instance, lithium and beryllium, because in fact, lithium and beryllium have such a low ionization energy, you don't even find them typically as a element in you don't find them as an element in nature. They're only in compounds because they automatically react. They lose that electron automatically in nature. And so it takes so little energy to remove the electrons for these. And that's why they're already in compounds in nature. But again, the point is, as you move across, the amount of energy it takes to remove an electron increases, right? As you move down the table, the amount of it gets those electrons get farther and farther away. So it doesn't take much energy to remove an electron. And that makes the elements at the bottom more reactive. They are more reactive down here. And I have a video we're going to watch, and we're going to be doing a lab next week. Again, you'll see that the elements at the bottom of a group, they all act similar, but the ones that are farther down are more reactive than the ones that are up high. Because again, they get farther and farther away from that nucleus, and therefore they more want to react with, they do want to more react. And so again, this is the ionization energy, the energy needed to take away one electron, right? And so that's what it is right here. And if you look right here, this is kind of makes sense. Look at here. The ionization energy, as the atomic number goes up, all right, look at the ionization. The ionization energy is very high for helium, neon, argon, krypton, xenon. And it's because they're already stable. They act similar. And you can see what do you think here's the element right before neon. Here's the element right before argon. They have a high ionization energy too. All right. And those are those halogens. They're right next to them. Those group 17. They have a high ionization. That means they want to keep that electron. They do not want to remove one. Whereas all the elements down here, those are all the group 1 elements, typically, except for hydrogen. But all those are the group 1 elements, and they have a low ionization. They really they want to get rid of it. It's like they don't care for that electron, right? Electronegativity. Electronegativity. If you look at this right here, this is the electronegativity. This is how much elements want to share an electron when it's in a chemical bond. Okay, the higher the number, the more they are attracted to the electron. The one that has the highest electronegativity is fluorine. Right, oxygen's got a high electronegativity. All of these got high. In fact, the ones that have more electronegativity are on the right side. All right. So on the right side has more electronegativity. They remember, why is that? Because they want to gain an electron. Fluorine really wants how many? It's got 7 valence electrons. It really wants one more. Chlorine's got 7 valence. They really want that one more. So they're very reactive, and they really want to bond with something. And when they share, they want to have it more. So is oxygen. They want to get that electron, especially in chemical bonds, when they start forming chemical bonds. All right. On the other hand, these metals right here, they have a very low electronegativity. If they're in a bond, they're like, you have the electron. I don't want it. And that's why they do what we're going to see is ionic bonds. They actually transfer the electron. They say, I don't want it. All right. And so that's what they're going to be doing here. And if you look right here, the electronegativity decreases as you go down. That because they don't have much attraction to the electron. Once you get further away from that nucleus, they're not going to have that attraction to that. And if you remember, again, one more thing is that all these elements right here in group 1, all these elements right here are not. This is group period 2. All these elements right here are, again, they're all in the same energy level, and you're increasing your number of electrons. And when you're increasing those electrons, they're closer, but they're the same distance from the nucleus, so they're closer to that nucleus, and so that nucleus pulls them a little bit more, and so they have a greater attraction to the electrons when they're in a chemical bond, because again, they're closer to that nucleus. All right, one more last thing here. So we were talking about that right here. Let me exit this real quick. All right. Let me pause the video for a quick second here. Okay. One last thing that you don't have this on your slides, but I do want to make an attention to it, is that the periodic table is mostly, if you look right here, most of it is metals. And what are metals? They're solids. Metals are typically solids, and they're good conductors of electricity. They typically have low amounts of valence electrons. All right, and they typically want to form cations. They're good conductors of electricity, good conductors of heat, and they can be made into wire, and they can be hammered. They're what we call malleable. Whereas nonmetals are either gases or brittle solids or liquids, possibly, but they are poor conductors of electricity. And so metals also are lustrous; they shine. All right, and metalloids have properties of a little bit of both. And so you can see these are the elements on the right side are the nonmetals, and the elements on the left side, like 3/4 about the 3/4 of the elements are metals. Of course, hydrogen is a nonmetal also. One note also about these metals and nonmetals is all the elements in the same group, they act similar, all right, because they have similar number of valence electrons. So they act similar. These are called the alkaline metals. These are the alkaline earth. All right, these are the noble gases. This is the halogens. And they act similar because they have the same number of valence electrons. And so they typically do the same type of chemical reactions when they do. These metals are typically very reactive, the alkaline metals and the alkaline earth. In fact, they're so reactive that they're not found in nature by themselves. They can be made in the lab by themselves. Right. The noble gases are very stable, right? And then the halogens are very reactive nonmetals, right? I just wanted to give you a little bit of that. That's just what I wanted to do. I'm going to tell you one last thing also here. Um, I need you for this is I'm gonna probably try to cut this out and put it at the beginning of the video if I can.